You couldn't, or just didn't have time, or what? Okay. I didn't. Andek, did you get a chance to try any of these?
No, sorry.
Then I don't feel it's very useful if I just give you the answers. How about this? We could do it in turns. So I could give you like 1 or 2 minutes to do the first one, then I can do the answer. Because they're all, with the exception of, like, okay, the first 3 questions are kind of short, but then it gets really hard from 4, 5, and 6. So let's see. Well, actually, let me get your opinion. What do you think, Siba and Andek? Do you just want to see the answers, or do you want to take turns? You're thinking for turns. And what are you thinking, Siba? Turns as well? Okay. So as soon as you finish question 1, give me a nod and I can do the answer then on the screen here, okay? Do you know what a harp is in the first question? You don't?
It's a musical instrument.
It is. Have you got any coins in your pocket? It's the Irish musical instrument on the back of your euro coin. Do you have any? I'll show you.
Oh, is it?
No, that's like a violin. It's that instrument. See this one here?
Oh.
That's the harp. It's a musical instrument. You know it, yeah. Do you have these back in your country, or is it an Irish thing? Yeah, it's not really a Middle Eastern instrument. They have a really old one in Trinity College, like hundreds of years, maybe even thousands of years old. I'll have to check it out. Anyways, okay. Whoops, sorry. Are you finished, Siva, or you're stuck? Okay, well maybe if I do the first one that could warm you up to help. Yeah. Are you confused or tired or both? Like, well, both, okay. Now I'm just trying to figure out what's the trouble with number 1. A girl is playing a harp. So she plucks a 30 centimeter long cord. So the string, she pulls it up like this, because we're told it's the first harmonic. Yeah? Now, this is 30 centimeters, and it's the first harmonic. So that is half a wavelength. So the wavelength is 60 centimeters. Or do you know what? Actually, the reason you're having trouble is because you need a piece of information which I told you last time, but I didn't say it again on this page. You need to know the speed of sound. Now, we did an experiment last time where we calculated the speed of sound. Remember the last question with the tuning fork? What was it, the answer? 340, wasn't it? Meters per second. Yeah. So I'm sorry, I can understand why you're confused now. So, do you know what? Rather than continuing, I'll just give you a few seconds here. Now that you know the speed of a sound wave is 340 meters per second, perhaps you can get the frequency now. Where's my pencil?
Sorry, what is the wavelength 60?
Huh?
What is the non-density?
Yeah, because if you look at that wave, how much of it do you have? You only have half of it. You only have the part that goes up, not the part that goes. So if half of it is 30, then a full is 60. Yeah. Rightio. Got a number crunched out there? You do, Siba? Yeah, what did you crunch out? 566 hertz. Super duper. Now I should tell you, for the exam, okay, the speed of sound isn't like a constant, like the speed of light or something like this. It's something that they should give you in the question. Do you understand? So it's not something you're supposed to use without them telling you its value in the question. It's a bit like specific heat capacity of water. It's 4120, but sometimes it's 4118, or sometimes they just write maybe 410. You know, they can change it slightly depending on who writes the exam. Yeah. Okay. Is that okay, Andek, number 1, and Siba? That's okay now? Alright, do you want to give number 2 a go? And again, you can use this if you need to, the speed of sound. Okay. Now, the only thing I'll tell you about number 2, just to remind you, is it's open at both ends. So, what does that mean? At each end, there's what? A node or an antinode? Antinode, very good, okay. And it's also the fundamental, meaning the first harmonic. It's definitely cold in the UK, minus 15.4. Okay, have you got number 2 done? Yep. So, open at both ends means it'll look like this. No. like this, vibrating up and down. So how much of a wave do I have in here? Half, isn't it? Yeah. Isn't it? Half a wavelength. Half a wavelength equals 40 centimeters. So a full wavelength equals 80 centimeters. And what do I want? The frequency again? So that is 340 over 0.80. So what frequency do I get for that fella? Was that 566 in the last question rounded off or exact?
26.
So it should be 567 then, if you round it off. And is that 475 rounded?
Yeah, 425.
475?
425.
Point anything? No. Okay. Right, now, what I'll do, number 3, I'll help you a little bit with number 3. Can I scroll down? So in number 3, a closed end organ pipe is used to make some music. So it's a pipe, an organ pipe is... Oh, actually, you probably don't know what an organ pipe is. Do you know what an organ pipe is?
Is it
No, what do you think it is?
a pipe or?
No, that's a piano. Unless, well, actually, no. Tell me more. You do play it like this, but what does it look like?
Looks like,
Yeah, what's different? It's like, it looks like a piano, but there's something different about it.
It's round.
doesn't have the big.
Yeah, and it has something else. It has these really big pipes coming out the top of it.
Oh, okay.
Yeah. I don't think you guys would know it because you usually see them in churches.
It's like a horror movie.
Or horror movies as well. Phantom of the Opera being one famous example, yeah. Anyways, you don't do music in mosques, do you?
No.
No. So that's, yeah. So anyways, in churches they use this instrument. So the third harmonic is formed at a frequency of 1100. What is the frequency of the fifth harmonic? So let's just practice here, guys, drawing the third harmonic. So don't draw this just yet, but we'll draw the first harmonic. And what should I have here? Node or an antinode? Should be a node, and here should be an antinode. So this would be the first harmonic. It would be a quarter of a wave. Then the second harmonic, oh my goodness, hard. Down, would be 3/4 of a wave. So, would it? Okay, anyway. The third harmonic is 3 times the fundamental, we said. And the fundamental is 1/4 of a wave. Sorry, so the third harmonic should be 3/4 of a wave. Let me help myself draw this. Okay. No, that's not 3/4. Hang on. Fundamental is this, 1/4. That's 1/4, right. The third is 3 of these, 3/4. Okay, 3/4. So, up, down. Okay, so finish on a down. Okay, so up, down to the middle again, and down to the bottom. Alright, so there to there is half a wave, and this is the other 1/4. So yeah, that's a 3. So that's a 3/4 wavelength. That's the third harmonic. And that corresponds to having a frequency of 1100. And the pipe is... Oh, you don't know. I don't tell you the length. Do I? No. Okay. And my question is, so what I'll do is I'll call that F3, the frequency for the third harmonic. And I want to know what is F5, the frequency for the fifth harmonic. And you don't know the length of the pipe. You can call it L if you want. Maybe you can work it out. I'll give you a minute to try. Yeah? So just remember, you can still use this formula, V equals lambda f, and you can still know that V is 340, okay? So maybe that will help you out a bit here. And if you like, I can do it in a minute, but let's see if you can figure it out. Come in! Ah, Matt, what happened to you? You got stuck in snow? What happened? Huh? Ah, so what you mean is the bed was nice and warm, and outside was cold, and it was just too hard to get up, huh? Did you get to finish the stationary wave questions in the workbook? No, they didn't either. So we're doing them together now.
Is this tutorial?
Yeah. Okay. Are you finished, Siva, or still thinking about it?
Sure.
Not sure what, if you're finished or what to do.
Not sure it's correct.
Okay. Well, what answer did you get?
1099.
1099? That's nearly the same answer as F3 though. Yeah, it should be a little bit more different than that. Like, it should be like different by about 100 hertz or something, you know. I better do this one now, huh? So look, you know this. The frequency for the third harmonic is 1100, okay? Frequency is V over wavelength. That's 1100. Yeah? Now that is equal to 340 over wavelength equals 1100. So the wavelength is 340 over 1100. So what's that, please? 309 meters. Okay. Now look, if it's the third harmonic, then how much of the wave is in the pipe? 3/4 of it. So if I want to work out the length of this pipe, I simply have to take my answer that's on my calculator and multiply it by 3/4. And what do I get? 232 meters. That's the length of the pipe. So the frequency for the fifth harmonic is equal to V over lambda, which is equal to 340 over lambda. But now we have to work out the wavelength for the fifth harmonic. Well, that should be 5 times the wavelength of the fundamental. And we said the fundamental is a quarter of a wave. Yeah? So you have to be careful now to get your numbers right here. Let me just make that a little bit clearer. Equals 340 over 5 times the wavelength. And the fundamental wavelength is a quarter of a wave, and a quarter of a wave is equal to that number there. So the wavelength would be 4 times that. So it's 5 times 4 times 0.232. And you see, that's not very easy to see. This is the fundamental wavelength. This is the length of the pipe. And if you multiply it by 4, you get the fundamental wavelength, because the fundamental wave, a quarter of it fits in the pipe. But then you multiply that by 5, because the fifth harmonic is 5 lengths of a fundamental. Because remember, that's what we said the harmonics behave like. Oh, you look shocked and confused and cold and tired and a little bit hungry as well. See, but you look totally shocked by this. If you have a question, please ask. The 5, 4 and that. Yeah, okay, let me do that again then, since it's a little bit quick. Alright, so, are we first question, are you happy with this length? Okay, so the second question is, imagine you have the fundamental wave in here. What would be the wavelength of this? Well, it'd be 4 times the length, because this is only a quarter of the wave. So you're happy that this is the fundamental wavelength here? Yeah? Oh, I think I actually made a mistake. Thank you, Siba. Thank you. No, okay. So, the fifth harmonic, how many waves would be in the fifth harmonic? It'd be 5. I'm saying it backwards, this is part of the confusion. I need to try and draw it on the side here. Right. There's the fundamental. Now we need to draw the fifth harmonic. Yeah. 5 quarters of a wave. Let me do my very best to draw that. There, 5 quarters. Now, what did we say the length of the pipe was? 0.232. That's the length of the pipe here. So I did make a mistake. Thank you. Here we want the wavelength here. Now, this wavelength would be 3/4 of 0.232, not 5 times it. I screwed that up. I'm also tired and hungry. Okay. Can you see? Because there's one wave, and that is 3/4 the length of the pipe, and we know the length of the pipe. So if I go back now, the denominator here is that over 3/4, 0.232. Okay. Is that okay, Siba and Namdek?
Why is it 3/4, not 5?
Yeah, it's 5/4. Well, my fractions. 1, 2, 1/4, 2/4, 3/4, 4/4, 5/4. So it's actually 5/5. You have 1, 2, 3, 4, 5 pieces in the pipe. 5 equal sized pieces. And one wavelength would be 4 of those pieces, so it's 4/5. Goodness sake. 4/5. What a disgrace. Okay. Yeah, it's 4/5 the length of the pipe is the wavelength here for the fifth harmonic. Yeah. Oh, but did I? Look, I'm just going to start this one from the beginning, okay? Because it's got so screwed up, and sometimes when something gets so screwed up, you just have to start it over, okay? So we'll just start it over. All right. I apologize. Okay. The third harmonic. So let me draw the fundamental. How big's the fundamental? It's a quarter of the wavelength. Okay. The third harmonic should have 3/4 of a wave in it then. So I'll try and draw 3/4 as best I can. So 3/4 of a wave would be up, down, and down to here. Okay. So we have 3/4 of a wave. That corresponds to the third harmonic. And what's the frequency of the third harmonic? It's 1100. And frequency equals V over the wavelength. Now what is the wavelength? We can work it out here. So I think this answer is still right. What do we get for the wavelength here? 340 over 110. Oh, what's that? 319. Yeah, this, huh? 0.309. Okay. Now that wavelength is not equal to the length of the pipe. In fact, what would be the length of the pipe? It would be 3/4 the wavelength, because your wavelength here is actually the length from here to the end of the wave, which would be to there. So if you got 3/4 of this number, you would get the length of the pipe. Is that what I did last time? Oh, good. So what was that? 232. Okay. Now you want the frequency for the fifth harmonic. That would be 340 over the wavelength. Now the fifth harmonic should have 5/4 of the wave inside of it. So let me try and draw 5/4. 1/4, 2/4, 3/4, 4/4, 5/4. Up, down, down, up, up. Okay. So what's the wavelength here? The wavelength would be the distance from here to here. Now you know the length of the pipe. So 1, 2, 3, 4. It's 4/5 the length of the pipe. So that is 340 over 4/5 the length of the pipe. I think that's what I had. Oh, good. Okay. So what's our final answer here? What do we get for this one? .831?
1831.
Oh, 1831 hertz then. Yeah. Oh, so 1832 then. Pretty messy, especially when you look at the picture I now have with my waves in it. Who can tell what that was? Can I scroll down? Yeah. Matt? Yeah. Okay, number 4. Number 4, a car is travelling 120 kilometers an hour between 2 transmitting radio towers. So here is tower 1 and here is tower 2. This is an interesting one. I like this one. I saw it in an exam a very, very long time ago. As you drive from this tower over to this tower, the radio signal gets stronger and weaker, stronger and weaker, stronger and weaker. So when we're talking about waves, this reminds us of what we were doing last time. It's kind of like the fringe pattern. But there isn't actually a fringe here, because it's not like the radio wave is being pushed through a slit. So actually what you're hearing is not the fringes, but you're hearing the nodes and the antinodes. So there's actually a wave here and another wave here, and they're forming a standing wave. And when you hear a peak, it's because you're passing through a part of the transmission where there is a antinode. And when the signal gets weaker, then you're passing through a node. So you're told in the question that the distance between the peaks, so that's between an antinode and an antinode, that is 43 seconds. And you could actually work out that distance, because you know how fast the car is going, 120 kilometers per hour. So by using your distance speed time triangle, the distance is speed multiplied by time. So that's 43 multiplied by, now 120 kilometers per hour, we need to change that into meters per second. So what do you get here, Siba, for the distance? You can give me a few decimal points. You have it on deck, yeah? 1,483.3. 3 repeating? So like this? Yeah. Now, how big is this wave? Well, if you have the distance between an antinode and a node, do you remember what we said the wavelength should be? You told me it last time when we did it. No? Matt, do you know? I think you know. There should be 2 of these. You guys actually told me this when we did it in class. I didn't need to tell you this. Because this is half a wave. So a full wave would be twice that distance. Are you forgetting things that you knew a few days ago that you told me? Okay. Trust me, if you watch the video from that lesson, this was your guy, you guys figured this out. So it's 2866.6, I believe. Yeah? Meters. Okay. So the frequency equals c over lambda. So that's what's the speed of light? It's on your calculator. What you could put in the constant. What is it, like C0 or something? Oh, your calculator doesn't have constants, does it? Does yours have it, Matt? I think it's 2.997 times 3 10 to the 8, is it? Or we sometimes just use 3.
3 times 10 to the power 8.
Yeah, 3 times 10 to the power 8 over 2866.6. So what do we get here? One oh four 653 hertz. Yeah? Which is equal to 104.6 hertz. Megahertz. 123 megahertz. Now the reason I'm doing it like this is because this is actually the way that they give frequency for radio stations. They give them as megahertz. So if you hear something like you are listening to FM 104 or whatever it is, What that actually means is you're listening on a frequency of 104 megahertz. Yeah.
Why
Is it not? 1, 2, 3. Oh, sorry. Kilo. Goodness sake, Stephen. Wake up. Kilo. Kilo. So I could have actually changed the question and said, what radio station is he listening to? So he's listening to FM 104. I think I will add that in for the next group. I'll add in a part 2. What is the radio station? Okay, continue. Matt, and continue. Yeah. Now it starts getting harder with number 5. A standing wave of frequency 1100 third harmonic is formed in a pipe. So hang on, let me just draw the fundamental, the third, and what's the other one? The fifth. Right, so how much of the wave fits in this pipe? The fundamental. It would be a quarter of the wave. Yeah, so there's a quarter of the wave here in the case of the fundamental. So I'll just write lambda 1. Now, in the case of the third one, how much of the wave fits into this pipe? It would be 3/4, lambda 2. And for the fifth one, it'd be 5/4, lambda 3, and we'll say lambda 5. So let me try and draw that 3/4. So 1, 2, 3. So that goes up, back to the middle, and down. And then this one here, 1, 2, 3, 4, 5. So up, down, down, back to the start, and back to the top then. Okie dokie? Yeah. Now, I give you some information. I say this frequency is 100 hertz, and then what's the other one? 1800 hertz then. Yeah? Right, my question is... What's my question? Do I not actually have a question? Okay, my question is, even though I say it, find what the error. So this question is a little bit more realistic. Because, do you remember I said, with these problems, it's not perfect. It's not like exactly 3/4 of the wave fits in here, or exactly 5/4. There's a little bit of an error at the ends. And the reason, does anyone remember what I said the reason was for this? It has to it's due to how thick the pipe is. It causes a little error at the end, okay? And we want to calculate that error. So look, if there was no error, this is what you would do. You would just say here, let's call the pipe length L. V, which is 340, equals lambda F, which is 1100. Yeah? And here you would say 340 equals lambda F. which is 1800. Yeah? Now, this would give you lambda, and this would give you lambda, and you could actually use both of them to get the L. So I've given you more information than you need, but that's if there's no error. What would be the length here? This would be 340 equals, so lambda, what's that? Yeah, so if you have lambda 3, how would you get the length of this pipe? So what would be the length here? Would it equal lambda 3? No, because lambda 3 is a little bit too big, isn't it? How much of lambda 3 would be the length of this pipe? There's lambda 3, goes out the pipe by a bit. How much of this wavelength would be the length of the pipe?
2.
Not 2 over, what would it be? Yeah, it'd be 3/4 the wavelength. Okay? Times 1100. And the same thing happens for the other one. Well, maybe you can tell me. For this wavelength, lambda 5, how much of it would be the length of the pipe? Very good. If you had the length lambda 5, and if you multiply it, you said by 5/4, you would get the length of the pipe. Yeah? So that would be 5/4 lambda 5 then. So actually I've written that backwards. I don't want to write this yet. Let me just get rid of that, sorry. Okay. So the length of the pipe is that, and the length of the pipe is that. However, this is the different part of this question. I said there's a small error. So in both these questions, both these lengths, you actually have a small error you need to correct. There's a little mistake in each of these. That's what I meant in the question. You see where I said there, the wavelength equals some length of the pipe plus an error. Yeah, something like that. Yeah? Yeah, it's okay. Yeah, so I just want to make sure you're all right with this so far. So, 340 over is lambda 3. Yeah, you can kind of feel like this is going to become a simultaneous, because what will happen is here you can say 1100 over 340, that's equal to lambda 3. And here you can say 340 over 1800, that's equal to lambda 5. You could get lambda 3 and lambda 5 from each of these. So what would be lambda 3? Let me see, that would be 4 over 3 here, and 4 over 5 here, and then 4 over 3 here, and then, what did I say here? 4 over 5 here. I multiplied by 4/5 and 3/4. So you have 4/5 L minus 4/5 the error, that's equal to lambda 5, which is 340 over 1800. And then on the top one you have 4/3 L minus 4/3 the error, that's equal to 340 over, thank you, 1100. Because I'm using, yeah, these two here. So you have two equations with two unknowns. Now let's clean these up a little bit. No, they're not. I was worried that they were the same. What should I multiply this one by? This one here. I should multiply it by 5, yeah? So I get 4L minus 4 errors equals this times 5. 340 times 5 over 1800. And then what should I multiply this one by? 3. 4L minus 4 errors. For flip's sake. Look at what's happened. What's gone wrong here? Can anyone spot a problem with my simultaneous equations? Can anyone see any problem with these equations? Can I solve these two? Why not?
Because they're both, I don't know what to say, but they will cancel each other out.
Yeah. The L and the E cancels. Ah. Alright, let's start again. I'm not likey. Question, Matt? Just give your teacher a moment to collect his thoughts and energy. Right, starting again. Okay. Third harmonic, fifth harmonic, length of the pipe here. If this is the third harmonic, how much of the wave fits in here? 3/4 of a wave. So we go up and down like this. We have 3/4 of a wave here, 3/4 of a wave. And this one here, the fifth harmonic, how much do we have? We have 5/4 of a wave. 5/4 of a wave, okay? Now, if I want to calculate the length of the pipe here, that would be... Sorry, let me... Do you know what? I give myself a little hint. Let me stick with my little hint here. If I want to calculate the wave of this here, and I know the length of the pipe, what would it be? Yeah, it'd be 3/4 the length of the pipe. And if I want to get the wave here, what would it be? If I knew the length of the pipe. Would it? If I knew the length of the pipe, what would be the wavelength? Would it not be 4/5? The length of the pipe? If I want the wavelength? One wave is here. And if I knew the length of the pipe, then the wave would be 4/5 of it. Yeah? Is that okay? Now I say in the question that if you do this, you'll be slightly wrong. There's an error here and there's an error here. So it's not perfect, okay? I give you, what do I tell you in the question? I give you the frequency. So we need to convert lambda into V over F equals 3/4 L plus error, and V over F equals 4/5 L plus error. Okay, what's the V for the first one? It's the same for both, it's 340. And what's the frequency? 1100. Okay, so when you're ready, maybe Siba, you could do that one, and Matt, could you tell me this fraction? 340 over 1800. So I have 3/4 L plus E equals 0.309. And then for the other one, I have 4/5 L plus E equals
0.189.
Alright, thank goodness for that. Now that's better. Sorry about that. Can we solve this simultaneous now? Yeah, we can. What should we do to solve this system? Minus them. Yeah? So 3/4 minus 4/5. What do we get?
Minus 0.05.
Why does it have to be minus? Wait, hang on. Matt, you told me it was 3/4 here. You lied to me. If you know the length of the pipe, how do you get the wavelength? It's not 3/4 the length of the pipe. What's the wavelength? The wavelength. 4/3. 4/3. 4/3. 4/3. Okay. Take 2. No, take 3. 4/3 minus 4/5. 0.53 repeating, is it? Yeah. L equals, and then when you take these two away?
0.120.
Say again?
1.112.
1, 2? Exact?
Wait.
Yes.
Yeah. Now, Just divide that answer by your 0.5333, and what do we get? 0.225 meters. That's the length of the pipe, and let's calculate the error. That would be, if I sub that guy back into, say, this one here, you get E is 0.309 minus 4/3 the length of the pipe. So what do you get there for this? It should be a small number.
9 times 10 to the minus 3.
So that's actually just 9 millimeters. So what you've said here is that the pipe is 22.5 centimeters long, but there's a small error when you're doing your calculations of wavelengths because it doesn't fit perfectly in. Now it's a very small error of just 9 millimeters. So this is why we don't usually consider it in our calculations, except for question 5, where I make you consider it. I'm sorry this is very messy, but I've seen this in the exam twice only, but it has come up twice.
So can you zoom out?
Yeah. You got this, Zero? Yeah. Matt? Andek?
Almost there.
Which part are you at?
The last part. Done.
Right. So the next one, microwave. Now, you might not know this, but the size of the microwave is actually not, you can't just make it any size. It's not like, in your kitchen you have an oven. That could be any size. But actually the microwave oven needs to be an exact size. And the reason for that is because, as you can see in the picture, what happens is a standing wave forms inside of it. Can you see it in the picture? So actually, if you made your microwave like 1 centimeter bigger, it wouldn't work properly. So this is why microwaves come in only certain sizes. Yeah? So, if you look at the picture, the microwave is 32 centimeters big. That's about the size of the microwave I showed you in class. Can you see there are 5 antinodes? 1, 2, 3, 4, 5. So part A, the first part is, what is meant by the term resonance? Does anyone remember what this word means, resonance? Anyone remember? No? Matt? Anda? No? Well, it's possible I didn't tell you. But anyways, I think you wouldn't remember because the last time you heard this word was in mechanics in semester 1. So, that's a while ago. I'll remind you. So this is, do you remember when we had the two springs? And one spring is vibrating like this, and then you grab the end of it, and you start to push it. Do you remember how you make this one vibrate more? What do you do with this spring? Same frequency. That's called resonance. When you have two things vibrating at the same frequency, they cause the amplitude to increase. This is called resonance. So you might say resonance is the increase in simple harmonic motion amplitude due to an external energy supplied at the same frequency. That's resonance. Got that? Yeah. I know you forgot the word, but now that I told you, do you remember? We did this in the mechanics. Yeah. Okay, can I go into part B? So what's interesting about the microwave is that you cause the water in your food to resonate. So you learned in chemistry and in physics, all the molecules are vibrating. And when you heat up the food, they move around more. But they're all vibrating at some frequency. Okay? Now, if you were to give the food energy at the same frequency that the water is vibrating at, what will happen to its amplitude? Increase. So this was what makes the food hotter. Okay? So part B. Where in the diagram will the food be heated the most? So when you look at the picture, where do you think the hottest parts of the oven will be? I would say it's at the antinodes, because this is where you get the most vibration in the wave. Yeah? Or no? Does that make sense? Okay, C. What is the wavelength here? Okay, so the wavelength would be, now if I look at the picture, how much of a wave have I got? 1, 2, 2, 2.5. 2.5. Isn't that right? 1 wave, 2 waves, and a half a wave. You look confused, Siva. No, it's 2.5, yeah? So the wavelength would be 0.32 divided by 2.5. So what's that then? .128 meters. That's the wavelength of the wave in the microwave. Okay, D. What is the frequency? Frequency equals C over lambda, which is 3 times 10 to the 8 over 0.128, which equals
2.34 times 10 to the power 9.
10 to the 9. Yeah, it's a big number, isn't it? That's the frequency. Can we convert that into something nice? 10 to the 6 is mega. 10 to the 9 is giga, isn't it? So it's 2.34 gigahertz. E. Therefore, what is the frequency of water molecules? So the water molecules are vibrating back and forth. At what frequency do they vibrate at? Well, it's the same, because that's how microwaves work. They operate at the same frequency as water, so to cause the water to resonate. Because all food has water in it. Like, I don't think you eat anything that doesn't contain water. Right? Can you think of any food you eat that doesn't contain water? It's not possible, right? Potatoes? They're actually, I think, 80% water, if you can believe that. If you could believe that. How much water in a potato? Yep, potatoes are 80% water and 20% solids. So it's actually mostly water when you eat a potato.
What about salt crackers?
But which one?
Salt crackers, aren't they? Popcorns?
Nobody has nobody has a web page about how much water is in crackers. What's crackers made from? Wheat, isn't it? Yeah. Anyways, the crackers would have water because the wheat would have water, because the wheat would have taken the water from the soil when it was growing. So, you see, you wouldn't have guessed that a potato is 80% water. Like, well, you know. But think about it. You're made of what? 70% water, right? And you could be food for some animal. So, you know, like most food would be mostly water. Yeah. I think that's interesting. Now, what we'll do now, I said I thought it would be a good idea if we look at some exam questions after we finish waves. So let's see what the waves look like in the exam. So you can open up Moodle. I'll open it up on the computer here too. One hour and 3 minutes for that tutorial. Oh my goodness.